Welcome to the deep dive. Okay, today we're heading out, way out, about 67 million light years away, to the constellation Cancer, the Crab, and we're looking at a galaxy that's basically refusing to fit in.
Yeah, that's a good way to put it. We're talking about NGC 2775. The sources we've looked at really paint it as a galaxy having a bit of an identity crisis.
An identity crisis. How so?
Well, it's got features from both of the main types of galaxies we usually talk about, spirals and ellipticals.
So it's mixing and matching parts.
Exactly. And that mix has astronomers, well, pretty divided on how to actually classify it. It's a real puzzle.
Right. So that's our mission for this deep dive then. We need to unpack the evidence, especially what the Hubble Space Telescope has shown us, maybe recently.
Yep.
And really get into why these in-between galaxies are so important for understanding how galaxies evolve over cosmic time. So for you listening, this is your shortcut to understanding some pretty complex stuff about galaxy life, maybe even death.
Absolutely. Let's start with what you actually see. Because the visual itself is where the contradiction begins. It's like looking at two different personalities smashed together.
Okay, let's unpack that. This structural puzzle. You mentioned ellipticals.
Yeah.
What part of NGC 2775 looks elliptical?
So right at the very center, the core is very smooth, very orderly, and crucially, it seems to be almost entirely free of gas.
Gas-free. Okay, and that's typical for ellipticals.
Generally, yes. Elliptical galaxies are often older systems. They've used up or somehow lost most of the cold gas they'd need to form new stars. So their centers tend to be pretty quiet, dominated by older, redder stars.
Right. Smooth, gas-starved. Sounds quite mature, settled.
Like an elliptical. That's the hallmark. Yeah, it suggests a very settled structure right at the heart.
There's always a but, isn't there? You look past that core, and the story changes completely.
Totally flips. Surrounding that quiet center is this big dusty disk, and it's not smooth at all.
Dusty. So, potential for star formation.
Exactly. The dust is clumpy, and it's sprinkled with these bursts of active star formation. We're seeing uneven clusters of really bright, young, massive blue stars.
Oh, okay. Young blue stars and dusky gas clouds. That sounds much more like a spiral galaxy.
It really does. That active star formation happening within a disk structure.
Yeah.
That's the classic signature of a spiral. Spirals need that reservoir of cool gas to keep building new generations of stars.
So NGC 2775 has this old, quiet, gas-free center, ringed by this dynamic, gas-rich, star-forming outer disk.
It's a strange combination, like you said, an old core with a brand new jacket maybe. A very active jacket.
And this brings us to something the sources mentioned, the perspective problem. Why does our viewpoint make classifying this even harder?
Well, think about it. We're stuck here on Earth, or near it. We only get one view of NGC 2775. We see it face on, more or less. So we're seeing a two-dimensional projection of what's actually a three-dimensional object. It's incredibly difficult to tell, just from this angle, if that outer structure is made of true, well-defined spiral arms that are just wound really tightly.
Like a compressed spring?
Sort of, yeah. Or if it's maybe just a thick, more featureless disk of gas and stars that happens to be forming stars. We can't easily distinguish between a tightly wound spiral, an S-type, and something flatter, more disk-like, which might lean towards the E for elliptical or S for lenticular.
Right, that makes sense. It's hard to judge the 3D shape from a 2D image.
Exactly, like
Right.
trying to understand a whole mountain range just by looking straight down from a satellite, you lose the depth.
So, because of that uncertainty, the scientific community is split.
Pretty much. Some astronomers focus on those young stars, that delicate-looking ring of dust and gas, and say, look, there's active star formation. It must be a spiral, maybe just a very tightly wound one. They'd classify it as a type Saw spiral, perhaps.
Okay, that's one camp. What's the other?
The other camp weighs that smooth, gas-free core more heavily. They look at the overall structure and argue it's probably moved beyond the classic spiral phase. They lean towards classifying it as a lenticular galaxy.
Lenticular. That's type S0, right? The one
Yeah.
that's kind of halfway between spiral and elliptical.
Precisely, S0. And this classification suggests it's not just a weird galaxy, but maybe a snapshot of a galaxy in transition, caught in the act of changing from one type to another.
Okay, so if we connect this to the bigger picture, this idea of the lenticular galaxy, the S0 type, seems really key here. It's like a bridge.
It absolutely is. Lenticulars share traits with both spirals, like having a disk, and ellipticals, often having less gas and star formation. And understanding them is crucial because, honestly, how they form is still a big open question in astronomy.
Right. So NGC 2775, being potentially one of these, could give us clues. What are the main theories for how lenticulars form?
Broadly, there are two main competing ideas, and the clues in NGC 2775 might help us figure out which path is more common.
Okay, lay out theory 1 for us.
Theory 1 is often called the fading spiral hypothesis. The idea here is that the galaxy started its life as a normal, healthy spiral galaxy full of gas and forming stars nicely in its arms.
Okay, a standard spiral. Then what happens?
Well, something interrupts that process. The sources suggest a couple of ways this could happen. One possibility is trauma, a major collision or interaction with another galaxy.
A crash.
Yeah, a galactic pileup. That could strip away the gas needed for star formation or heat it up so much it can't cool down to form stars anymore. The spiral arms would essentially dissolve or fade away because the fuel line got cut.
Ouch. Violent. Is there a less dramatic version?
There is. The galaxy might just run out of gas naturally. It slowly uses up its internal reservoir of star-forming fuel over billions of years. No big crash needed. It just sort of fades out.
Starves itself.
In a way, yes. The star formation dwindles, the bright light stars in the arms die off, the arms become less distinct, and you're left with a smoother disk around the central bulge, a lenticular galaxy.
So either a violent stripping or a slow starvation leads to a faded spiral. That's theory 1.
That's the essence of it.
What's theory 2 then? The evolving elliptical. That sounds like the opposite direction.
It is, sort of. In this scenario, the galaxy starts out closer to the elliptical end of the spectrum. Maybe it was a smaller elliptical or one that formed early with less initial gas.
Okay, so starting quiet.
Right. But then, later in its life, it manages to pull in new gas from its surroundings. Maybe from a gas cloud drifting by or by consuming a smaller, gas-rich satellite galaxy.
So it accretes material, it snacks on something.
Exactly. And if it pulls in enough of this external gas, that gas can settle into a disk around the original elliptical-like core. And if that gas cools down enough...
Star formation kicks off in the new disk.
Precisely. You'd end up with an older, smooth core surrounded by a newly built star-forming disk. That looks a lot like a lenticular galaxy, too, or even something like NGC 2775.
But wouldn't that process of pulling in gas be messy? If it just slurped up a random gas cloud, would the resulting disk be as neat as what we sometimes see?
That's a really good point, and something for you, the listener, to think about. If the gas accretion was just chaotic, you might expect a very disorganized, clumpy disk.
Right.
NGC 2775's star-forming ring, while maybe not perfectly smooth, seems relatively well-defined. This tidiness might make the fading spiral idea seem a bit cleaner, perhaps, but we definitely know galaxies do accrete gas, so theory 2 is still very much in the running.
Okay, this is where it gets really interesting, you said.
Yeah.
Because there's actual physical evidence of, well, a rough pass for NGC 2775.
Yes. This pushes beyond just interpreting the visual structure. The sources highlight some pretty compelling evidence, found not just in visible light, but by looking for specific types of gas.
And this evidence points toward transformation, maybe violence?
It strongly suggests a history involving significant interaction. The most dramatic piece is a huge, incredibly faint tail of hydrogen gas.
A tail, like a comet.
Sort of, but on a vastly larger scale. This tail stretches almost 100,000 light-years around NGC 2775.
Wait, 100,000 light years? Isn't that roughly the size of the entire Milky Way's main disk?
It is. Just pause and picture that. A stream of gas, the ghost of some past event, as large as our own galaxy, wrapped around this other galaxy.
Wow. Okay, that's not just a little puff of leftover gas then. That's monumental.
It absolutely is. And the existence of a tail like that is a classic sign of what astronomers call tidal stripping.
Tidal stripping. Sounds painful. What does it mean?
It means NGC 2775 likely had a close encounter, or maybe even a direct collision and merger, with at least one other, probably smaller, gas-rich galaxy in the past.
Right.
As that smaller galaxy got too close, the immense gravity of NGC 2775 would have stretched it out, pulled it apart, like the ocean tides on Earth, but with gravity tearing a whole galaxy to shreds.
And the tail is the leftover debris from that shredded galaxy.
Exactly. It's the stream of hydrogen gas pulled out from the victim galaxy, now orbiting NGC 2775 as a relic of that encounter. It's pretty clear evidence of galactic cannibalism, basically.
So what's here seems pretty direct. This violent merger history is probably why the galaxy looks so strange today.
That's the strong implication, yes. The past trauma, the merger, likely shaped its current hybrid appearance. It forced a transition.
it used violence to change its identity, essentially.
That's one way to look at it. Whether it was originally a spiral whose arms got ripped off or messed up in the collision, or maybe an elliptical-like object that gained this gas and disk from the merger. The tale proves that external events played a huge role. It wasn't just quiet internal evolution.
Which connects back to those two formation theories for lenticulars. This favors a more interactive, less passive formation route, at least for this galaxy.
It certainly supports the idea that mergers and interactions are key drivers in shaping how galaxies look and evolve, pushing them away from those neat, simple categories.
Okay, this leads us perfectly into the latest news. The sources mentioned a new Hubble observation, dated September 23, 2025. There was an image back in 2020, but this new release adds something critical.
That's right. This isn't just about getting another pretty picture, though Hubble images are always stunning. This is about targeted science. The new data focuses specifically on a very narrow wavelength of light.
Narrow wavelength, what kind?
It's a specific shade of deep red light, known technically as H-alpha, hydrogen alpha emission.
H-alpha. Okay, why zoom in on just that particular color? Why is that the key?
Because H-alpha light acts like a beacon for active star formation. It's not just general starlight.
How's that work?
Well, think about massive, young, hot stars. They blast out enormous amounts of high-energy ultraviolet radiation.
Right, the really energetic ones.
That UV radiation hits any surrounding clouds of hydrogen gas, which is the basic fuel for stars, and it energizes the hydrogen atoms. It makes them glow.
Okay.
And one of the specific characteristic colors or wavelengths they glow at when energized like this is H-alpha, that deep red color.
Ah, so if you filter everything else out and just look for H-alpha light?
You are basically seeing a map of only where stars are being born right now. You filter out the light from all the billions of older, quieter stars, the background noise, as you called it earlier.
Got it. It's a star nursery map.
An excellent way to put it. It gives astronomers a really precise picture of the distribution of current star formation within that strange, dusty ring structure of NGC 2775.
So how does this H-alpha map help settle the classification debate between tight spiral and fading lenticular?
It comes down to the pattern and intensity. If the H-alpha map shows that star formation is happening vigorously all across the disk, maybe in slightly clumpy but definitely widespread patterns.
And that suggests the galaxy still has plenty of fuel and is actively behaving like a spiral, just maybe a tightly wound one.
Exactly. It would lend weight to the still functionally a spiral argument. The spiral arms might just be hard to see clearly in normal light, but the star formation is still chugging along.
Okay. But what if the H-alpha map shows something different?
Conversely, if the H-alpha reveals that the star formation is really patchy, maybe concentrated in just a few isolated knots, and overall quite sparse, quite weak.
Then that would suggest it's running low on fuel. The spiral arms really are fading out.
Precisely. That would be strong evidence that it's well on its way to becoming, or already is, a lenticular galaxy, a system that's shutting down its star formation.
So this new H-alpha data gives them the detail needed to see past that perspective problem we talked about, to judge the vigor of the star formation.
Yes, it lets them probe the current activity level, which is a fundamental indicator of a galaxy's type and where it sits in its evolutionary journey.
So pulling this all together, what does NGC 2775 really mean for us, for our understanding? It's clearly more than just a classification headache for astronomers.
Absolutely. It's a fantastic real-world example of cosmic evolution in action. It beautifully demonstrates why that simple spiral OR elliptical picture we often start with is, well, it's just too neat for the messy reality of the universe.
It's showing us the transition state.
Exactly. It's a snapshot of a galaxy caught mid-change. And that change seems driven by a combination of factors potentially violent past mergers, which we see evidence for in that huge hydrogen tail.
Right, the galactic cannibalism.
And also the slower and maybe inevitable process of just using up the available gas fuel needed to make new stars. We're watching a galaxy caught between its past and its future.
And it really highlights that galaxies aren't these static, isolated islands. They interact, they collide, they change each other profoundly over cosmic time.
That's a crucial takeaway. Their histories, their evolution, are shaped just as much by these external encounters as by their internal processes.
Okay, so let's leave our listeners with something to chew on. Based on everything we've discussed about NGC 2775, its maybe violent past, its current transitional state, this reliance on mergers and gas supply, if this galaxy's fate, its ultimate identity, hinges on these processes, what might that imply about the long-term future of all spiral galaxies, including our own Milky Way?
That's the big question, isn't it? Are these beautiful spiral structures with their active star formation just a phase? A long, glorious phase, perhaps, but ultimately destined to fade.
Destined to be smoothed out by mergers, starved of gas, and eventually transition into lenticulars or even giant ellipticals over the vast expanse of cosmic time.
It's definitely something to ponder. Are we just seeing spirals in their prime, knowing that the universe's clock keeps ticking towards a potentially quieter, smoother end state for most galaxies? Something to think about next time you look up.